All right, thermodynamics. Earlier in the course, we dealt with the first part of thermodynamics, heat changes during chemical reactions, right? So now we're dealing with the whole topic, right? The rest of it. Thermodynamics versus kinetics. All right, so we've had a kinetics topic at this point, and kinetics is concerned with how the reaction rate's changing as the reaction goes from reactants to products, and how can we affect rate of reaction, speed it up, slow it down maybe, and looking at what affects rate of reaction, we're able to deduce mechanism, what pathway the reactants have to go through in order to get to products. Uh, Thermodynamics isn't concerned with that. Thermodynamics is concerned with position of equilibrium. When the reaction stops, no more forward rate of reaction. When the reaction stops, how many reactants did we lose? How many products did we make? So in chemistry, we're interested in whether a reaction will go. Go means when the reaction stops, do we make a lot of products? Um, and occurring in some way that we get the products in a timely manner, right? We don't want to wait around 10,000 years to have the reaction finish, which can happen with some reactions. So in other words, if it's so slow, you're not getting your products, it's not useful. If we have an unfavorable equilibrium where we're not getting a lot of products and that's what we want, it's not going. All right, as we've used this terminology before, right? A spontaneous process is product favored, meaning when the reaction stops, I lost a lot of reactants, made a lot of products. Whereas non-spontaneous, I had a lot of reactants left over, very few products made. Being spontaneous or not has nothing to do with the rate. We can have a very slow reaction that makes a lot of, basically loses all the reactants and makes products, but it happens really slow. So again, speed of reaction has nothing to do with position of equilibrium. All right, so there's laws, right? Facts about heat uh, and reaction. All right, so at this point, we've explored the first law, law of conservation of energy, right? Energy is not lost during a reaction, right? It's transferred from one form to another. So if I lose potential energy, I release kinetic energy. Again, with this topic, we're not concerned with the hump. The hump is about kinetics. We're concerned with how much heat was released during the chemical reaction. Right? So it's exothermic, right? You've lowered the potential energy of the system, you've gone to a more stable state. Well, that implies a spontaneous process. All right, so with exothermic reactions going to a more stable place, that implies the reaction is going to go. Whereas with a endothermic reaction, you got to put heat in to make it happen. You're going to a less stable place, a higher potential energy place. That implies non-spontaneous, a reaction that doesn't make very many products before it stops. Our expectation, therefore, is if we have an exothermic reaction, the reaction is going to go. We're going to get a lot of products. Well, not always. A lot of reactions are endothermic, but yet they're spontaneous. They go to completion or they lose most of your reactants and make products. So there's another component to whether a reaction happens or not that we're missing here. Just, outside of what happens with the heat, there's something else. Also temperature, right? At one temperature, a reaction can be spontaneous. At another temperature, it's not. So temperature has something to do with whether a reaction is spontaneous or not. All right, so ice melts spontaneously, temperatures above 0 degrees Celsius. That's an endothermic process. You always have to put heat in if you want to melt that crystal, rearrange that crystal. So it spontaneously happens, even though you're putting heat in. Ammonium nitrate, if you look at your solubility rules, anything with ammonium ion soluble, anything with nitrate ion soluble. But if you look at the delta H, you have to put heat in order to make this happen. So a very spontaneous reaction at 25 degrees Celsius, but endothermic. So we can have endothermic reactions which are spontaneous. We can have exothermic reactions that are non-spontaneous. We can have endothermic reactions that are spontaneous, and we can have endothermic reactions which are non-spontaneous. All All right, so all examples exist. All four of these examples exist. All right, so as far as heat goes, if you have an exothermic process lowering the potential energy of the system, that implies a spontaneous process. So how does a reaction that's endothermic become spontaneous? Well, it's related to this thing called entropy. Entropy is a measure of the randomness or disorder of a system. So the second law of thermodynamics says that a process is spontaneous if it leads to an increase in the entropy of the universe. All right. So how does that work? All right, we'll talk about it. Entropy is related to probability. The most probable outcome is the more disordered outcome. So what is probability? Well, a probable event is one that has many ways of occurring, whereas an improbable event is one that only has one way of occurring. There's only one way to win the lottery, right? To get the right series of numbers. Many ways to not win the lottery, right? All different kinds of numbers you could get. There's only one way to win with the lottery, right? Get the right sequence. So it's the same thing with entropy. There's lots of ways to become disordered, but there's very few ways to become ordered. So the way we look at this, or the classic example of is an expansion of a gas into a vacuum, right? That's something that's spontaneous. If I let a gas go, it'll flow into the empty space. Whereas what it won't do is flow out of the empty space and create a vacuum. That's a non-spontaneous process. So how does that work? Well, open up the gap between these two containers, right? The one where there is no gas particles and one where there is. The most likely outcome is that you get an even distribution of gas between the two particles. Many ways of achieving that. Whereas the gas particles only ending up in one container, right? If I just leave them sit, is a very improbable event. There's only one way for this to occur. All the gas particles end up on one side and not on the other, just through random motion. So why is the spontaneous process the one that gives equal number of gas molecules in both flasks? It's the most probable outcome. It has the most ways of being achieved. So if we just look at a single gas particles, what's the chance that the gas particle ends up in the left bulb? Well, it's a 50-50 chance, right? There's two outcomes, right? You could either be in the right bulb or the left bulb. So just by letting the gas particle move around, you have a 50-50 chance that the gas particle ends up in the left bulb. All right. N represents the number of molecules, right? So if we're talking about one gas molecule, the way this works probability-wise is it's the inverse of 2, right? The two outcomes raised to the n power, right? The number of particles. So raise the 1 power. So 50-50 outcome of ending up in the left bulb. If I introduce two gas particles now, what's the chance that both of those particles end up in the left bulb? Well, these are the options, right? You can end up with both of them on the left, the green one in the left, the blue one on the right, or the blue one on the left and the green one on the right, or both ending up in the right. So, and the probability of having them both end up in the left is 2 raised to the 2 power, all right, or a quarter chance, 0.25% chance that both of them just through random motion end up in the left. So a less likely outcome. If I have 3, what's the chance that all the balls end up in the left bulb just through random motion? Well, there's only one outcome where that can occur, where there's 3 ways that you can have 2 on the left, 1 on the right, 3 ways in which you could have 1 on the left, 2 on the right. And again, there's only one outcome with them both ending up on the right. So again, the one with the even distribution, or the more even distribution between the two bulbs, has the more likely outcome. Whereas if you raise the one opportunity for all those balls to end up in the left container, you end up with an 1/8 of a chance, and so on. So if I'm dealing with a mole of gas, it's 2 raised to the n power, right? 6.02 times 10 to the 23. So basically, there is no chance, just through random motion, that all the balls end up in one container. That's such a small likely outcome. We don't consider it. So that's non-spontaneous. So what is the probability that if you have 4 gas molecules, they'll be equally distributed between the two bulbs? Only one way for them to end up to be in the left. There's three ways to end up in the left, one in the right. Two ways to end up in the left and two in the right. One way to end up in the left, three ways to end up in the right. So if we're looking at an even distribution, that has the greatest possibility for occurring, the most ways to be achieved. All right, so 6 out of 16 possibilities. So it's the most likely outcome that you get an even distribution between the two bulbs. So entropy is based on probability. The most probable outcome is the one where things are most disordered, evenly distributed. So an ordered state has a low probability of occurring, a small entropy, whereas a disordered state has a high probability of occurring, high entropy. All right, so as far as states of matter go, right, a solid state is the most ordered state, right? Particles are locked into a crystal with a repeating pattern, so that is a low entropy state. That's a less likely outcome. More likely that you're melted, right, where you get this sliding motion past each other. And then the most disordered state is where you're in the gas state. This is the most probable outcome, right? Particles going where they want to go. So most disordered gas, less disordered liquid, the least disordered solid. All right, so it's possible to determine the absolute entropy S of a system, whereas with enthalpy, we could only measure changes, right? We couldn't measure what the absolute value of heat was for a system, but we can do that with entropy. We can find a place where there's perfect order. All right, so we can talk about how disordered you are compared to that position of perfect order. The unit for delta H was kilojoules. The unit for S is joules per Kelvin. So if we're talking standard conditions, we can talk about delta S's, or not delta S's, S's, right? Again, absolute values. How disordered a system is at standard conditions. So that'd be joules per Kelvin per mole, whereas delta H naught is kilojoules per mole. Standard state, 25 degrees Celsius, 1 atmosphere pressure. Or is it 0 degrees? I forget. I think maybe you're right. It's 0 degrees. Is it 0? I forget. Anyway, so S values, right? So just like with delta H, you can look up how disordered a system is at 25 degrees Celsius and get the S's of formation of the reactants, S's of formation of the products, plug it into products minus reactants, and get the change in entropy, how disordered the system's becoming. So we'll be doing that later.